Hello and welcome to PCMINR.com, and you're watching this video on important concepts of electrostatics for grade 12 by Sonal Gupta. And I again repeat that the harder we work, the more luck we seem to have. And in this video, we are going to talk about the electric field on the equatorial line of an electric dipole. Now, what is the equatorial line? See, an equatorial line of a dipole is the line which is perpendicular to the dipole and of course passing through the center of the dipole, right? So, if I say I have the charges minus q at the point A and plus q at the point B, and O is the midpoint, and if 2a is the length of this dipole, the total length, then A and A will be both the halves. So, O is the midpoint, and this line which is passing through the center of this dipole is going straight up perpendicular to the axis. So, this point we can mark it, say P here, is our observation point which lies on the equatorial line of the dipole. So, a line that passes perpendicular to the axial line and it passes through the midway between the charges is our equatorial line. Now, let's see what all will be the distances and the fields here. So, if we consider R to be the distance of the point P from O, then what is going to be AP and BP? Since it's a right angle triangle, because this is perpendicular, therefore both of them can be found out by the Pythagoras theorem. It will be an equilateral triangle because P is equidistant from both the sides. So, this side and that, both the sides would be A square plus R square. That's going to be the distance of these points. Now, what will be the electric field at P due to the charge at A? That's going to be Q upon 4 pi epsilon naught times R square. Now, what is the distance R square? It's A square plus R square root, and so when we square it, it becomes square, of course. And this electric field is directed towards the charge, negative charge. Therefore, it's here along PA. So, I'll write it here along PA. Now, what would be the electric field at P due to the charge at B? That's going to be Q upon 4 pi epsilon naught R square plus A square, because see, this time the magnitude is absolutely the same. It's just the direction which varies, because for the positive charge it will go away from the charge. So, it's towards, say, PD. So, if my electric field due to the plus Q charge is same magnitude but along PD, therefore, what should be the net or resultant magnetic electric field? Now, electric field at the charge at the point P, see, because these are inclined at an angle theta, right? So, these are inclined at angle theta, therefore, we can resolve it into components. So, with the x-axis, the angle made is theta for this and this component. And as you can see, the vertical components, if we draw the vertical components, they are going to be cancelling each other, because for vertical component for this one, that's along PD, goes up, and the vertical component for this one goes down. The magnitude being equal and opposite, it would cancel out. So, we can write here that the vertical components of EA, right, the vertical components of EA and EB, they cancel out, but we will be left only with the horizontal component. So, they both will add because they are in the same direction. So, whether you take it for EA or for EB, it's both in this direction. So, therefore, the total electric field is going to be the sum of the components, the horizontal component. So, that's going to be 2 times E in A cos of theta. So, whether you take EA or EB, it's the same thing. So, I write twice of EA cos of theta, the horizontal components, they add up to give the resultant electric field at the point at the point P. So, substituting the value of EA, so we have the resultant electric field on the equatorial line as twice of Q upon 4 pi epsilon naught A square plus R square into cos of theta. So, that gives me twice of Q into 1 upon 4 pi epsilon naught, I'll write it as K upon A square plus R square. And what is the value of cos of theta? So, we can find out cos theta from here. It's base upon hypotenuse. So, I'll substitute the value of cos theta is A, the base, upon R square, that is r square plus a square raised to the power 1 by 2. Right, and when I put this value, what is 2q times a? The product is p, so I get p k upon a square plus r square. The powers get added, so it's this whole square, and sorry, this won't be whole square, this is not whole square, so we have a square plus r square plus 1 by 2, so that gives me 3 by 2. So we get the resultant electric field on the equatorial line as pk upon a square plus r square raised to the power 3 by 2. Now for the special case, that's for a short dipole, again a square would be ignorable. So I would get the electric field on the equatorial line of a short dipole to be p times k upon, this would give me r cube. So we find that the electric field on the equatorial line is pk upon r cube, whereas the one we had on the axial line was 2pk upon r cube. That means if we talk about a short dipole, then the electric field on the axial line is going to be twice the electric field on the equatorial line, and both will vary inversely as the cube of distance. That's an important relation between the electric field along the equatorial and axial lines. I hope you find this video helpful. Please like us, subscribe us and follow us on Instagram and Facebook at PCMINR.com. Thank you for watching.